Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain.
There are a lot of blink and you missed it things that are hard to see here on Earth. From the sight of a particularly bright meteor during a star party, the acrobatics of a dolphin leaping out of the water on a ferry trip, if you are looking the wrong way and at the wrong moment, you miss everything. In looking at the sky, what it means for something to be short lived is a little different, but the idea is the same. As we scan across the sky, we see lots of fully formed stars, which can live for billions of years. We see a fair number of things that last hundreds of millions of years. But the shorter lived the phenomena, the harder they are to find examples of in the sky. Catching planets in the process of forming is one of those short lived phenomenons that we're struggling to catch. This is a double problem. We have to catch something short lived, and we have to catch it with just the right geometry that we can see the planet separately from the star. Of the 4,000 exoplanets of all ages so far found, only 15 have been directly imaged by a telescope as a dot beside a star. Now, with a combination of hard work and a bit of luck, a still forming planet has been imaged orbiting an orange dwarf star, PDS 70, just 370 light years from Earth. A mere hop away. This is one of 3 planets in this system, and according to lead researcher Yifan Zhao, this is the youngest bona fide planet Hubble has ever directly imaged. Zhao developed novel data processing techniques that allow the research team to carefully separate the light from the star and the planet, allowing them to determine the planet is continuing to slowly grow as it circles at a Uranus-like distance from its star. Now we just need to find a whole bunch more of these at different ages so we can measure growth rates at a variety of different times. This work is published in the Astronomical Journal.
Like Beth said, short lived means a lot of different things in the context of the universe. Planet formation goes on for millions of years, and the effects of phenomena like solar flares might last for only hours or maybe minutes or seconds. Researchers studying Mars using radars on both the Mars Express and Mars Reconnaissance Orbiter have periodically experienced weird blackouts in their data where radar returns stop returning. Since studying these weird blackouts wasn't the goal of taking radar data, understanding what is causing this has been a back burner problem that may finally be understood. In research led by Mark Lester and including some of our Planetary Science Institute researchers, Than Putzig and Matthew Perry, it has been determined that solar energetic particles can ionize the lower atmosphere on Mars, and this partial ionization prevents healthy radar returns. Basically, an active sun means no radar for science from the Sherrod and Marsis radar instruments or for their scientists. While this is no big deal, the research can be done at different times. It is problematic if the radar can't get through. This also means that communications with future robots and humans also won't be able to get through and will be disrupted periodically by solar activity. This is just one more problem that will need to be sorted if we want to keep humans safe on Mars.
The words short and rare really are a matter of context. Female PhD astronomers, hi Pamela, they're rare, but we see them. Humans were short lived, but we see them. Still there, Pamela? When it comes to the shortest lived and rarest events, I have to say the moment that a bunch of molecules become a living cell, that may be one of the rarest and shortest lived things we really wish we understood. While I doubt we'll ever catch life naturally coming into existence that way, we'd like to figure out how to force this to happen in a lab. And doing a lab experiment like this requires researchers to understand where the stuff of life actually came from. In new research published in Science Advances and led by Yoshihira Furukawa, researchers announced that the organic chemistry necessary to create the amino acids that build life could have used wildly available materials found in the early solar system. This work required the team to study the compositions of meteorites that contained essentially locked samples of the building blocks of planets. This allowed them to see what kinds of reactions took place and hint at what reactions, foremost type reactions, if you want to know, might have led to, well, us. After the break, we're going to switch from things that create life to things that are a bit more dangerous. Tsunami. Stay tuned. As a planetary geologist, I'm more well versed in ways of destroying life than in creating it. This next story is your daily reminder that the universe is trying to kill us, and it doesn't even need rocks from outer space to do so. No, no, the universe can rely on Mother Earth to do her fair share. When I taught a natural hazards class, one of the things I had to explain to my students were the hazards that go along with earthquakes. After all, I live in earthquake country, but beyond the normal shaking and rolling land waves we get here in California, there is one type of hazard our quakes aren't generally responsible for: tsunami. These deadly events are usually the result of subduction earthquakes, those ones where one tectonic plate is going under another plate. Subduction earthquakes are common around the Pacific Ocean in what is known as the Ring of Fire. The same plate interactions that cause those volcanic arcs we talked about a couple of weeks ago also come along with massive quakes. And when one of those happens, the upward thrust of the topmost plate causes water to be displaced upward. That water has to go somewhere to keep everything even. And like ripples in a pond, it spreads out from that point of origin, creating a tsunami. As the tsunami approaches the shoreline, the water pulls back from the shore while the wave front gets compressed in the shallower depths, building up what we think of as a wall of water. In the 2011 Tohoku earthquake, the wave height at the shore was on the order of 10 meters, causing massive amounts of destruction along the coast and even farther inland. The water will keep moving, and because these huge ripples bounce, they'll go back and forth for a while. The 2004 Boxing Day tsunami occurred as a result of a quake off the coast of Sumatra, and over 200,000 people died as a result in countries as far away from the epicenter as Kenya and Tanzania. Unfortunately, we tend to learn lessons only when they are particularly harsh, and scientists realized that this extreme death toll was partially due to the lack of warning systems in place in the region in 2004. So they quickly increased the number of deep ocean assessment and reporting of tsunamis, or DART, buoys in the region, and created a network that now includes over 60 of the floating sensors. This also includes 12 new buoys over the Kermadec Trench near New Zealand, which is a particularly fast-moving subduction zone and prone to frequent high-magnitude earthquakes. And they got to witness, in the resulting data this year, an extremely rare event: a triple tsunami as a result of three closely spaced, very large earthquakes, all over magnitude 7. These earthquakes occurred on March 5th, 2021, off the coast of New Zealand, all within 1,000 kilometers of each other and several hours of each other. Each quake spawned its own tsunami, and the buoys recorded the changes in wave heights as each event passed by. Since the data is analyzed in real time, local authorities were able to keep the public informed of any pending threats and to cancel the warnings when the threat had passed. Because the buoys are in place, authorities canceled the alert more than 4 hours earlier than previously possible. And these buoys don't just save lives and time in the South Pacific. The tsunami generated by all these subduction earthquakes can travel swiftly across the Pacific and Indian Oceans at speeds in excess of 800 kilometers per hour, and they can reach distant shores in countries like Chile and the United States. During that 2011 quake, several lives were lost in California, and the property damage in marinas along the coast was extensive. So here's hoping for more buoys in more places to save more lives. Coming up next, Pamela will go back to beginnings and talk about the reionization of the universe. Stay tuned.
From Earth destruction, let's jump to universe construction. A recurring theme is, how did everything start? Like, we know there was a big bang, things expanded and cooled for 400,000 years, and then stars and galaxies started doing their thing, and their light cleared out the universe. Where we get stuck is, did those galaxies most responsible for clearing out the universe grow from massive collapse of stuff into massive galaxies, or through the formation of a myriad of tiny galaxies? We know galaxies formed both ways. The universe is all about yes and. But in this particular whodunit, we're learning that while there was massive galaxies out there clearing out their surrounding gas and ionizing everything with ultraviolet starlight, it may have actually been the small galaxies scattered everywhere that actually did the bulk of the work. Researchers led by Nathan Egan and publishing in the Astrophysical Journal show that one tiny galaxy is clearly doing a lot to blow out the universe. This galaxy is Pox 186. It's a compact system with about 100,000 solar masses of massive stars. Where it's located just a couple billion years after the formation of the universe, its light is ionizing the neutral gas all around it. And part of how it's doing this isn't just the ultraviolet light, it's actually the stars as they explode as supernovae are pushing out the gas. Their ultraviolet light is breaking free of the galaxy, and all around this galaxy, the universe is becoming transparent. Now, little galaxies like this were the most common. And just like a single bonfire will do a really good job lighting up one part of a field, if you fill that field with 100 campfires, you can light so much more. And it looks like these little galaxies, like Pox 186, they lit not just so much more, but everything. And because of them, we can look back to the earliest moments of the visibly transparent part of the universe a few billion years after it started. And once the JWST maybe launches, we're going to go with maybe, because superstition at this point. It will be able to see just what was forming. After the break, we're going to be back to talk about what is time anyways. Trying to understand the timescales that things happen in our universe is something our little human brains sometimes struggle with. From the formation taking moments to go from nothing to all the energy and matter that ever is and ever will be, to 400,000 years before we actually start to be able to see anything, to millions and billions of years for that gas to form the first stars. Time, it's vast and sometimes seems to stop. In fact, there are days right now where I have to ask, what is time anyway? This morning, as I worked on this show, I looked around my office and realized it is fossilized to January 2020. Calendar on the wall still says December 2019. Yearly passes attached to lanyards on the bulletin board, 2019-2020 year. Everything just kind of stopped as every day became Blur's Day. As humans, we don't see millions and billions of years. We measure the passage of, well, depends on the human, just what you say. Today, to many people, is measured from the moment of waking to the moment of sleeping and then waking up the next day. Even if that today happens to span multiple calendar days. A year for a teacher or professor is September to August. Time. How we divide it up, at least, is just an arbitrary set of decisions. For the purposes of science, a day is the amount of time it takes for a single point on a world to go from noon to noon, except when it isn't. Here on Earth, we rotate such that the sun moves across our sky daily for folks not at the poles, and we have a close to 24-hour day. For Uranus, the planet is flipped sideways. So the solar day and the orbital period are the same, 84 Earth years. But relative to the stars, a day would be measured in Earth hours. Of course, exactly how you measure that rotation of a gas planet is a bit hard. What do you measure the rotation against? With Saturn, folks have decided to measure a day based on the ripples the planet's rotation causes in the rings. By the way, Saturn's day, it's 10 Earth hours and 33 minutes long. Gas planets, they're just kind of hard to sort.
Filed under why is this so hard? It turns out that cloud covered solid planets can actually hide the length of their day pretty effectively, too. While Venus is in many ways a twin to Earth, similar size, similar original composition, the world had a rather catastrophic history that isn't explained by just its closer distance to the sun. Understanding what happened actually requires understanding how Venus rotates and how that reflects its internal structure. The thing is, we can't see its surface. While orbiting satellites can get some information on its day length from radar images, their fast orbits and the influence of Venus's shape on their orbits make precision hard. In fact, past measurements didn't match each other. So scientists started hitting Venus with radar from Earth, and over long periods found, quote, the new radar measurements show that an average day on Venus lasts 243.0226 Earth days, roughly 2/3 of an Earth year. What's more, the rotation rate of Venus is always changing. A value measured at one time will be a bit larger or smaller than a previous value. The team estimated the length of a day from each of the individual measurements, and they observed differences of at least 20 minutes, unquote. When your average day is 243 Earth days, a variation of 20 minutes actually isn't a lot. But how Venus got that way, that is a serious mystery we can't solve today.
Well, we can't solve everything. We can still celebrate what we can solve and what we can see and what it inspires us to create. And we here at CosmoQuest know that many of us are still trapped in our houses and we just generally need something to bring us joy. And this July, we are going to bring you CosmoQuesticon, a virtual event that is going to celebrate the discoveries of the 1980s with all its neon colored acid wash gene glory. From the space shuttle to the Voyager missions to everything in between. We're going to rock like it's the 1980s. Not quite as cool as saying 1999, but still, Purple Rain, it came out in the 1980s. Come celebrate with us. You can get your tickets now. We're going to be doing the main stage events free to all on Twitch, and there is going to be a second stage and a backstage lounge where you can meet guests, all available through Discord, all virtual to keep everyone safe. Check it out, cosmoquest.org.
As a reminder, we celebrate May the 4th around here. It's a somewhat silly holiday, but we are all geeks and nerds, and so we get a little silly with it. In this case, May the 4th is a play on Star Wars. May the Force be with you. And since about the 80s, speaking of, people have kind of acknowledged this as sort of an unofficial Star Wars event. And now it's sort of an official Star Wars holiday. And around here, we count it as a work holiday. So there won't be any shows from us that day. But if you're interested, I will be doing some other things over at the SETI Institute. And you can check all of that out at SETI.org. So join us again next week when we come back.
For now, this has been The Daily Space.
You can find more information on all of our stories, including images, at dailyspace.org. As always, we're here thanks to the generous contributions of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.